The last speaker is Jun Wu, Professor Jun Wu. He's very well known in the community of topology optimization, very active researcher. And he's an associate professor at Delft, University of Technology in Netherlands. Before joining Delft, he was a Marie Curie postdoc at DTU, where Niels comes from. And he obtained his PhD in computer science in TU Munich, and also a second PhD in mechanical engineering from Mayhem University, and received many recognitions for his contribution to the field of topology optimization. And nowadays, he's focusing on computational design and digital fabrication, and his talk is about this, about how use topology optimization to optimize the process of additive manufacturing for smart material. So thank you for coming, Jun. The stage is yours.
Thank you for the very kind introduction. And I would also like to thank the organizers and Daniel for the invitation and for putting together this wonderful event. It's a great honor to be here. As introduced, my name is Jun. I'm an associate professor from Delft University of Technology. My background is computer science, mechanical engineering, aerospace engineering. But for the past 8 years, I've been working in the Faculty of Industrial Design Engineering. In many other places, industrial design is either part of mechanical engineering or part of architecture. But in the Netherlands, as well as in Belgium, and probably in some other places, industrial design is a separate discipline. And in industrial design, we care about mechanical performance, but we also talk about human perception. And I'm talking about this because some of the examples, the motivation is not for mechanical purpose. And today I'm going to talk about space-time topology optimization for smart materials and advanced manufacturing. I will focus more on the advanced manufacturing part. Space-time topology optimization is a new name we gave to describe the type of algorithms or the type of problems that arise from advanced manufacturing. As a disclaimer, it has nothing to do with relativity or with Albert Einstein. Thanks to Niels for giving a good overview of topology optimization. I also have one slide to explain this field from my own perspective and why I am so interested in this field. Here on the bottom left, you see a beautiful design from Joris Nama, is a Dutch designer. He created this beautiful bone chair back in 2003, so 20 years ago. To some extent, it's hard to tell whether he designed this chair or he discovered this chair. The reason I say so is because he didn't manually sketch the geometry. The geometry came off computer algorithm. So it starts from a solid block, and in this block, he identified where the forces will be applied when a person is sitting on top of it. And on the ground, he specified where the leg should be fixed on the ground. And starting from there, the algorithm, in an iterative process, removes material where it is less relevant. At the end, it comes up with a very beautiful organic design. Due to the similarity in the algorithm, like to only place material where it is necessary, also due to the appearance and the similarity to the bone, it is given the bone chair name. So this is topology optimization, and increasingly in the past decades, because of industry players in this market, it is getting popular with the name generative design to highlight that the design is computed with algorithms instead of manually sketched by the designer or by incremental optimization. So it's a very good example of form follows function, where the function is the performance requirement and the form serves this function. What I find extremely beautiful about this topology optimization is that it transforms the manual design process into a mathematical problem, and the mathematical problem is where to place material and where not to place material. The applications or the development has been mainly driven by aerospace and the automotive industry, where engineers strive to reduce the weight of mechanical components. That translates to less fuel consumption and less greenhouse gas emissions. So, for example, in the design of Airbus A380, topology optimization was used to design the wing ribs, reducing 500 kilograms, which is huge. Relatively recently, in a science fiction, The Midnight Sky, produced by George Clooney in 2020, topology optimization was used to design a futuristic space station, as you see from this picture. These days, if you Google topology optimization plus additive manufacturing or 3D printing, you will find many this type of organic shapes. They are all designed by this algorithm and produced by additive manufacturing. As Niels introduced, topology optimization has been under intensive development for almost 4 decades, but only in the past 10 or 15 years, topology optimization has been really recognized by industry. One of the reasons is because look at these complex geometries, they are very difficult to produce, but with additive manufacturing, it becomes possible. Not without challenges, but it becomes possible. If we zoom out from the mechanics part to the product design, and we know when we design products, we consider not only the mechanical performance, but also many other factors. For example, how this product is going to be produced, whether it can be produced and how it will be produced, and what kind of materials. And today, let's talk about smart materials and how can we take these material properties into the design process. And from industry design perspective, we also care about user experience. Do people like this design or not? For a component in a car, probably don't care too much whether it is beautiful or not. But if it is a consumer product, let's say if it is a chair, we do care about whether it is comfortable, whether it is beautiful. My research has been primarily focusing on the design of hierarchical structures or structures that are composed of microstructures, shown on the left, and this is a multi-scale structure, and also considering manufacturability, whether it can be produced in the intended quality. As 2 side tracks, I also work on high-performance computing, and here the intention is to support the development of this algorithm in 3D because it becomes very intensive. And the last one is about user experience, whether it looks good. So today I'm going to focus on manufacturability and manufacturing process modeling, but before that, I will quickly introduce the other 3 directions. The first one about computational framework. This video shows the computational design and optimization of an entire airplane. We are very much inspired by the effort to optimize the wing, but it's only a half of the plane. So here we try to optimize the entire airplane. And this opportunity is in collaboration with colleagues from aerospace faculty. They designed a V-shaped blended vehicle. And here we test if we have this different unconventional airplane layout, how should we design the internal structures? So here we developed this computational framework to get an understanding of how the structures in this V-shaped airplane would look like. Moving on to this human perspective. So here you see 2 chairs. One of them was designed with this top up, and the other one is a slightly modified version. The person sitting on top of it is the same. And my question to all of you is, which one do you find more beautiful? I see people pointing to the left, people left and right. Yeah, so here, the one directly come from topology optimization is the one shown on the right-hand side. And the left one is modified by our students who received training on aesthetics, and they know principles. And these principles are very difficult to describe mathematically, but they have this understanding. Based on that understanding, they modify the shape. And we did these experiments to 12 pairs of examples, and in 11 out of 12, the modified version, most people consider more aesthetically pleasing, which tells there is potential to improve the aesthetic quality of topology optimized results. Even though we don't have mathematical description, and we are working on how we can enable designers to influence the design process in order to come up with a design that is mechanically optimal at the same time having good aesthetic quality. Moving on to the multi-scale topology optimization, and this has been my research since I started to work on this topic 10 years ago. Here on the left-hand side is the cross-section of the femur. In the middle is a higher resolution topology optimization in 2D with these mechanical boundary conditions similar to a person sitting or standing. And these microstructures automatically grow from this grayscale evolution. And on the right-hand side is a 3D printed. Of course, the algorithm is applied to 3D. The algorithm just extension with no modification. Here are some more examples. In order to show the internal porous structures, we designed, on the left-hand side, we designed a chair which is made of 9 slices. It is laser cutted, not 3D printed. And it was, on the left side, it was my daughter, already 7, quite a few years ago. It's totally different. On the right-hand side is the application of this algorithm to design the internal cabin of this flying V concept. And it was exhibited at Dutch Design Week in 2019. In this infill optimization, we have to discretize the geometry with a very fine granularity in order to create detailed geometric details. It is computationally very intensive, so later we had been working on how we can use dehomogenization or geometry-based dehomogenization to more efficiently come up with high-resolution structures. Again, an industry design application of a chair on the left side, so it illustrates the mechanical boundary condition, and in the optimization, the optimizer tries to decide where should we place material, and if we place material in which orientation it should be placed. And here we get a discrete field representing the orientation of cross structures. Then with geometric algorithms, we compile a continuous geometry from the discrete directions. And on the right-hand side is a fabrication with stereolithography. This 2D example illustrates how it works. So on the left side is a design domain, and in the middle it shows the optimization results. So it gives where this lattice structure should be placed, and if it should be placed in which orientation, as well as the density or the sparsity of that microstructure in that particular area. And an important technical contribution here is to compile from a discrete direction field into a continuous structure, as you see on the right side. Here, with this geometric algorithm, we can compile a continuous geometry where it is following the sparsity coming from the homogenization-based optimization. An experimental validation on why we need multi-scale structures. So this is a 3-point bending test. On the left side, on the bottom is a standard topology optimization, which is solid, and on the top is with this multi-scale or 2-scale structure. And on the right side is the setup of the mechanical test. This is the force displacement curve. So the slope indicates the stiffness. If you compare these two types of structures, we can see the solid structure is slightly stiffer, but the lattice structure has twice Buckley node. And this proves some benefits of using lattice structures. Here are some more examples. The second one is the application of topology optimization to the design of implant. So here we design microstructures that change porosity, and they are well collected. D is a bicycle saddle, where we have designed a geometry which can be printed with either extrusion-based printing. On each layer, it is one slice, and the cross layers, it is self-supporting. And we also worked on soft robotic raper. I'll come back to that at the end of my talk. Now move on to the manufacturing. So Much of this research is inspired by recent advances in additive manufacturing, especially in robotic fabrication, where the robots have 5 or 6 degrees freedom. It can deposit material almost arbitrarily. And this gives a lot of flexibility in the design process, but there are also some unique challenges. So this robotic manufacturing process is a direct energy deposition process. It's called a wire arc additive manufacturing. Essentially, it's a continuous welding process using robotic arms. It has been used to design components for industries like aerospace, maritime, where you demand large structures of 1 meter or several meters. So from architecture, space, maritime, and oil and gas industry. And Netherlands is pretty strong in this area, and there are 2 industrial partners in the Netherlands specialized in developing this large-scale manufacturing. This was before I went to TU Delft. It was 2015. This is an illustration. It's Photoshop, not a real photo. It's a vision from MX3D, the industry a startup in Amsterdam. In 2015, they made this beautiful futuristic scenario. The invention in the future, the bridges can be produced by robots that move on top of it. In the Netherlands, we are not short of bridges, but just as a demonstrator of this technology. Of interest here is not only the robotic fabrication, but also the design. The design was inspired by topology optimization. It is a very lightweight design. So it was 2015, the dream, and 6 years later, the bridge was produced and it was installed over a canal in Amsterdam. And on the right side, you see the inauguration of the bridge by the Dutch Queen. And if you compare these 2 pictures, you immediately recognize it is not the same bridge. The one on the left side, lightweight. The one on the right-hand side, beautiful as well, but it's very heavy. It took 4 robots for a period of 6 months, continuously producing, consuming in total 4.2 tons of stainless steel. So it's very heavy. And you may wonder why they decided to move on to a different design. There are many logistic challenges as well as technical reasons behind it. So the challenges in this additive manufacturing process or metal additive manufacturing in general, because the metal powder or wire is melted at very high temperature, 1,200 degrees, and there are multiple phase transformations, and because of this multiple phase transformations as this repeated heat input and thermal cycle, there is residual stress. And this residual stress would manifest itself during manufacturing. It can create distortion, and sometimes this distortion can be so big, the manufacturer has to deform the shape back in order to continue the manufacturing process. And this residual stress can also manifest when the component is detached from the build plate, as shown in the middle. And if it doesn't deform, it doesn't mean everything goes well. It may create a crack or micro crack. So if we look back into the design of the bridge, normally in design manufacturing, these 2 processes are decoupled. By decoupled, I mean when we design something, we design a structure, and then we move on to manufacturing, and then we realize it couldn't be produced, or it couldn't be produced with high quality, then we return back to design and to modify in order to make sure it can be produced. But even when it can be produced, it doesn't mean there are no defects. If you look at the thermomechanical process into this manufacturing process, it very much relates to the structural design, but also relates to the process. By process, I mean according to how the structure is produced piece by piece and layer by layer. So if you look at the branch on the right side, let's say the black area has been produced. In a manufacturing process, you could decide, should I go to this branch and then move on to the next branch or to the next branch, or should I propagate simultaneously across multiple branches? So there are many decisions, and this manufacturing process will influence the thermal history of the material, and which will influence the material microstructure development and the residual stress. Since this residual stress depends both on structural design and process planning, the question we asked is, can we incorporate this process planning into structural design? This is very difficult because if the structure has not been designed yet, how can we plan the process? So this is what we propose. On the left side is topology optimization. We have mechanical boundary condition. The component is fixed on the left-hand side. There's force on the right side pointing downwards. And in topology optimization, it solves the problem of where to place material. So in topology optimization, in 2D, you will work at something like this. To the end is a structure optimized for stiffness using the minimum amount of material. And what we call space-time topology optimization is, if we look at the topology optimization, it tells where to place material, but it doesn't tell in which order the material should be placed. And this is what we address in this space-time topology optimization. It determines when to place material at which location. So here, this time dimension is indicated by the different colors. So here, on the left side, the structure should be produced from left to the right. And if you look at the color, it indicates starting from one quarter and gradually move on to the right-hand side. And in this way, it makes sure structural integrity during the manufacturing process. So with this space-time optimization, we try to formulate structural design and process planning in a unified framework where we can evolve both the material layout and the materialization sequence in the same manner. This was a result back in 2020. So the artificial problem we had in mind is to design a bridge to be built with robots that move on top of it. And we assume the robot is moving from left side to the right-hand side. And during each of the intermediate stage, the bridge should be stiff enough to support the location of the mobile robot. And this is the result, seeing the robot is jumping around. So it's quite futuristic. We don't really expect it can be realized very soon. But nevertheless, this is very encouraging. It shows for the first time we can optimize the sequence before the structure has been designed. So how it is realized? So in topology optimization, we represent the material distribution with a pseudo density. The pseudo density ideally should be either 0 or 1, indicating where there is material, where there is no material. And in space-time topology optimization, we introduce a second set of optimization variables indicating in which moment it should be materialized. And this time value is a continuous value. This is in contrast to the structural layout, which is a binary. And from this density and time field, we can segment the component into different layers or different intermediate stages. And upon these intermediate stages, we evaluate its mechanical performance and make sure it satisfies the design intention. So this is kind of the workflow. On the left, we have density field, we have time field. And from these two, we compute the intermediate structure. And on the intermediate structure, as well as on the final structure, we evaluate whether it meets the performance criteria, and this will drive the evolution of these two fields. So this is the specification of the example where the robot is moving on top of the bridge. Here, the design intention is that when the structure has been fully completed, it should support a force on the bottom right, and during manufacturing, the structure should support the movement of the robot. So this is similar to the one I have just shown. And in a computer, we can imagine different way of producing. Let's say we have a robot which can jump top to the bottom, and you can also imagine if there are two robots which simultaneously fabricate this bridge, and then, of course, this manufacturing capability will require adapt of the structure, sequence, and the design. As I said, we don't expect this will be soon in the coming years. More relevant for industry is to use this space-time optimization to address residual stress and distortion, which they are facing in the practice. So here we are using this to design the sequence of a component in a way after fabrication, the top layer should remain flat. Here it shows a comparison between typical planar layers and on the right-hand side is with the optimized curve layers. So there's a big difference in the amount of deformation if we fabricate the component in these two different sequences. And numerically, it is 2 orders of magnitude difference in distortion. Again, we have evaluated this algorithm in 3D to have this component where we are particularly interested in on the right-hand side, there's a rectangular shape, and we want that shape to remain vertical. So this shows the fabrication sequence. And here we have prescribed number of intermediate stages to be 10, and in the algorithm we can increase to 20 or even to 100. That will give more fine control of the manufacturing process. So challenges ahead for this research direction, we are particularly interested in analyzing the convergence of this space-time optimization, where if we discretize into 20 layers or 100 layers, how does the optimized solution corresponds to the discretization resolution? Whether it converges to something or whether it can improve even further as we refine the design and the time sequence. Move on to the second one, specifically for wire arc additive manufacturing. For now, we are using an inherent stream model, which is computationally very efficient, but is known to be less accurate for predicting residual stress. So we are developing, we hope to develop more efficient and accurate model to represent the manufacturing process. And also, we have to consider manufacturability constraints. So we are exploring the fact that the robotic arms can deposit material almost arbitrarily, but in practice, industry prefers to have constant process parameters for better control of the material microstructure. So we are trying to incorporate geometric as well as process-related constraints into the simulation and optimization. The computation is intensive, so we are also working on extending this to 3D and using hierarchical approach or multi-resolution approach for representing the sequence and to accelerate the optimization. On the right side, we are very much interested in experimental validation, because to the end, this numerical algorithm, if it only is fancy in computer, is not convincing enough. And for that purpose, we are working closely with industrial partners as well as colleagues in the material science department to understand material properties and to eventually demonstrate the benefits of this space-time topology optimization. I was thinking if this can be finished in the coming years very soon, there's other challenges, more exciting challenges ahead. For example, if we look, so the bridge I have shown are engineering structures, but if you look into nature here, this is a bridge in India. It's a bridge made of living roots. These materials, they grow over time, and they have the capability to sense and to actuate. They don't do autonomously. Of course, there's some manipulation by the villagers to help build a stronger bridge. The question is, how can we take into account the sensing and actuation and the growing of the material properties into the design process? I find this very interesting. A last slide before the conclusion. Besides topology optimization, I have also worked on soft robots with PhD and as well as master students. On the left side, it was a soft gripper designed by Robert Schaff. He's now an assistant professor at Hong Kong University. We didn't apply topology optimization yet because we spent a lot of time to understand what is the requirement for the soft robots. In topology optimization, if we can measure the object function, there's no guarantee, but it's very likely we can we can do something with optimization. But when we move on to application, it is more challenging for us to understand how do we quantify the performance. For example, in the software grapher, we want it to be stable, but it took us quite some time to understand where the stability comes from, or where does the instability comes from. So this animation shows, or this video shows, we redesign the structure, not by topology optimization, but by engineering design in order to improve the grasping stability. Let me see how I can. The video is pretty. Well, it's a 2-minute video. I will just show part of it. So I will. So this is a standard grapher actuated by pneumatically, and this is an improved grapher where the stability is improved. The reason of instability in this case is these soft fingers, they are easy to bend. We want it to be easy to bend so we can easily actuate it. But when it is too flexible to bend, it can also twist. And our fingers, human fingers don't twist. But soft fingers, they twist. So we design a stiffener to prevent the twisting while not affecting the bending behavior. On the right side is a graduation project by Sangda, very talented master student. He designed this robotic, soft robotic fish inspired by tuna, because tuna is known to swim really, really fast. So by mimicking the movement and by innovating the actuation process, we are able to achieve very high speed, which can compare to the size, in relation to the size of the fish, it was the fattest. It can swim 1 meter per second. And this design is made open source, and it has been reproduced in some other institutes around the world. Conclusion and final remarks. The time dimension introduces some new challenges and interesting research questions for topology optimization. The time dimension can be related to the manufacturing process, can be related to the growing process of living material, or to the actuation, the time-dependent actuation of materials. And we have conceptually validated this space-time optimization framework by designing the structure and at the same time planning the fabrication sequence. There is a lot of future work waiting for us to build more accurate additive manufacturing process model, as well as experimental validation. And lastly, if we go beyond this engineering static structures, we have to consider, for example, in soft robots and living structures, I consider the most challenging is to build efficient and accurate mathematical model to predict the behavior of these soft structures, as well as to identify representative performance criteria. Because if we want to use optimization to design, we need to know what we are optimizing for and whether it really is most relevant criteria. With this, thank you for your attention.
So thank you very much, Jun, for the nice presentation. Iago, we have time for a short question, 2 questions. Is there any question in the audience? Yes. Wait.
Okay. Thank you very much. Very impressive talk. I'm just interesting the soft gripper. So that's what you are talking about. So the last time, the final. For example, in soft hand, maybe its advantage to can cope with it can cope with not only one target but also multiple objects. I mean, for example, so the human hand can pick up so the pencil,
Yeah.
and so they can pick up so the, for example, so the pet bottle and so on. We can so the human hand can so the pick up so the various objects.
Yeah.
So the in so the design method, so the optimization methodology, is it possible to so the to cope with such kind of so the versatility? So the can you consider so the such kind of sorry, kind of so yeah, so the kind of so the hand can pick up so the not only one, but also many various objects. Yes.
Yes. So I understand your question as how can we design software robots which can grasp a variety of objects with different shape, different stiffness. I think this is software robots has an advantage to be flexible, and you can geometrically it can enclose different shapes. As I mentioned, in this, when we come from computational mechanics to this particular application, we have to understand how do we measure the grasping capability over a variety of shapes, and that part is missing.
Okay.
Yeah.
Understood.
Yeah.
Well, I think.
No.
Thank you so much. It was interesting. The first question about the human-centered design. You mentioned the aesthetics. Is it me? Okay, sorry. Oh, thank you so much for the presentation. We're interesting. The first question about the human-centered design, when you mentioned about aesthetics, can you still explain it in mathematics? I didn't get if you can translate the aesthetic part in mathematical model.
No, we don't have a mathematical model yet.
And do you think in the future is it needed or not?
I think it is. If there's a magic equation to describe whether a shape is beautiful or not, I would be very excited about it. But I don't think there is such an equation. Well, there is some very abstract equation to say the simplicity and the complexity, they should be balanced. That's one of the principles in design. Then the question is, how can we measure simplicity and how can we quantify complexity? So I think philosophically it makes sense, but to really describe it in a way the algorithm can understand is challenging. I think the way to address this is there are two directions. One is to say we build an interface, allow the designer to influence the algorithm and co-design the final structure. And this would require computation to be run really fast to allow interaction, and also how can we intuitively manipulate an algorithm. That is also a research question. And the second direction, which I consider promising and which also meets with the current hype on artificial intelligence, is if we, as consumers, we are trained because we see different shapes, different products, advertisements, and we have a sense of beauty. And if we can develop this sense of beauty by looking at different shapes, the computers might also be able to do that. So if we feed a lot of data to the computer, telling the computer which one more people prefer, potentially there's a data-driven approach to incorporate these aesthetic properties.
It's just a thought to share with you. Just linking with one of the challenges that Monodon is proposing. So at some point, Abdon said about underwater operational stuff, right? Like manufacturing underwater.
Yeah.
So I was thinking that your approach is probably super nice for this space time optimization.
Mm-hmm.
As at some point, you have something that is evolving by increments of time.
Yeah.
And you can adapt to the environmental changes, right? So that's something you have got in mind, like not only in terms of I understand residual stresses due to thermomechanics, etc., but also to take into account that, for example, yesterday Mokaran was saying, differences in winter and summer, or if you are underwater, something can change, right?
Yeah, yeah, yeah. That's the idea. So to consider how the structure experienced during its life cycle, and the conditions can vary over time, and how we can incorporate that into the design process. So it's more multi-objective, considering a variety of application scenarios, which also somehow relates to the soft robotic gripper, how to handle different objects. Yeah. Yeah. Thanks for the question. Yeah.